Hello everyone, welcome back to our Calculus 2 course. Today I'm going to cover two sections of 8.2 and 8.3. They are about more applications of integration. So let me start with 8.2. We'll be talking about the surface area of revolution. 8.2, area of surface of revolution. Okay, so what is it all about? Say you have a curve, okay, in general. You have a curve. And say you want to rotate about a line. Could be a horizontal line, could be a vertical line. I'll just give you an example right here. Say I'm going to rotate this curve. Function is f of x, okay? Y equal to f of x, this one. And rotating about this line. You're going to have something like this. It looks like a ball. Okay, rotating. And what we are looking for in this section is we want to find a surface area of that curve when you're rotating about the line. Okay? So the whole idea is what? The surface area going to calculate was we're going to chop the curve up into many little curve, and we rotate that little piece around this called axis of rotation, okay? Around the axis of rotation. And we're gonna calculate the surface area of that little bit only. And then we add up all the little area together, we have the area of the entire surface of rotation. Does that make sense? We have a curve, okay? We are rotating that curve about the axis of rotation. We're gonna have a revolution right here, okay? And what we're interested in this section is we want to calculate the surface area, the surrounding area of that revolution. So what do? The strategy is we chop it up into many little rings, if you see, little rings. Like this. Okay? And then we're going to calculate the surface area of that little ring. Okay? We have many little rings like that. We just add the area of all the little rings together. We have the entire area. So, since this is a little rings, we can think of it like a strip, a band. And the area is calculated by what? The circumference times the thickness. The thickness here is ds. Okay? That's what we learned in the previous section, 8.1. ds was square root of 1 plus dy over dx square times dx, or it's of dy is going to be 1 plus dx over dy square times dy, either way, because ds actually comes from square root of dx square plus dy square. That's what we had last time. This is the ds that we have right here, the thickness. And we're going to time what? The circumference of that circle. Okay? The circumference is 2 pi r. So this is called dA. The little area of that little band right here is calculated this way. So the entire area is the sum of all that little area is going to be integral of 2 pi r ds, and of course 2 pi is a constant, you can bring it out. So this is really the main thing. That's what you all know in this section. Okay? So the idea of calculating the surface area is you chop it off to many rings. Okay? We calculate the surface area of one ring at a time. The surface area of one ring is 2 pi r, which is the circumference, times the thickness. That little bit right here is ds. Okay, ds. Alright? And then you time the circumference. You have the area of that little band, that little ring. And then you add all the little rings together, all the areas of the little rings together, you have the total area. So the formula that you want to focus on in this section is area is 2 pi r ds. R is the radius. This is r. Oh, I gotta draw it better. R is the radius. The distance from that point that you jump into the axis of rotation. Okay, so it depends on from you have horizontal axis rotation or vertical axis rotation in count 2 right here, then we're going to calculate R. Okay, and we will decide whether to use dx or dy. But this is the main idea before I give you the example. Okay, so let's start with an example. Let me just choose an easy function. I'll show you many versions of it, different problem using the same example. Say I got the curve y equal to x squared. Say x from 1 to 2, make it easy. 1 less than or equal to x, less than or equal to 2. So this is the curve. Draw it. This is a problem, obviously. Look like this, okay? 1 right here, 2 right here. So x from 1 to 2, then y gonna run from 1 to 4. I think x is 1, y is 1, so 1 is less than or equal to y, less than or equal to 4. Okay? Now, this is my curve. First problem. Okay, first problem. What if I want to rotate that curve? The curve right here. About the y-axis. This is the x-axis. This is the y-axis. I want to rotate that curve about the y-axis. I want to rotate the curve about the y-axis. Well, it's going to be right here, all the way to here, right? Rotating. So I want to calculate the surface area. Can you imagine that? I want to rotate that curve about the y-axis, but x vary from 1 to 2, and I want to calculate the surface area of that thing. So let me try to emphasize, make it look, hopefully look better. Because, okay, this is the surface area that we're looking at. Okay. The formula that I gave you was area is equal to 2 pi integral R ds, okay? You can write 2 pi outside and inside of the integral because those are constant. So I need to calculate two things, to find two things. R, which is the radius of revolution, of rotation, and ds. ds is, we know right there, from 8.1. So if we are rotating about the y-axis, you have any point on the curve. When x runs from 1 to 2, the radius is the point right here is x comma y, okay? So the radius is the distance to the axis of rotation. In this case, it's going to be x. This is x right here. This is y right here. So in this case, the radius r equal to x. And since r equal to x, I know the variable I'm using in here is going to be x, so I'm going to choose the first formula right here. So it's going to be 2 pi integral r is x, and ds is going to be square root of 1 plus dy over dx. So I got to calculate dy over dx in here. Dy over dx is equal to 2x, right? Derivative. So this is 2x squared and then dx. And then I'm going to calculate this integral. And this is, oh, by the way, the boundary, x runs from 1 to 2. Okay, so this is 2 pi integral from 1 to 2, x square root of 1 plus 4x squared dx. And this integral is pretty doable. You can let u sub u equal to 1 plus 4x squared. And you have du is ax dx. That should take care of the problem. All right. Now, let me move to another problem, okay? So I'll let you finish the problem right here. The rest shouldn't be too hard. Okay, try another one. I'm going to use the same function. But this time, I'm not rotating about the y-axis anymore. I'll be rotating about a different axis. And of course, we have a new problem with new surface area. Okay. This is my curve again, y equal to x squared again. X you run from 1 to 2 again. Okay. Now I'm going to rotate that piece of curve right here. This curve. About the vertical line, say y equal to -1, for example. This is a line y equal to -1. All right, and this is the axis of rotation. I'm going to be rotating the curve y equal to x squared about that vertical line. All right, So you're going to have something like this. Alright, from here to here. So you have a bigger bulb, a wider bulb. Okay. You see that this is going to be a new area to calculate, a new surface area, this one. Alright, see that? The axis of rotation is not the y-axis anymore. It now is the vertical line y equal to -1. Still a vertical line, but not the y-axis. And we have the same formula. A is equal to 2 pi integral of r ds. ds is the same as before, but the thing that changed now is the radius. The radius is the distance from the curve to the axis of rotation. This is the radius r. Okay, so if the point right here, this is x, this is y, and the radius is not x anymore. The distance from here to here is x, and the distance from here to here is 1, right? So the radius now is x plus 1. You see? X is from here to here. This is x. X. And this is 1. Right? 1 right here, x right here. So the distance is x plus 1. Okay? As you can say, x minus -1. That's how people think of it. Okay, so the problem now is two pi integral of x plus 1, which is the radius, times square root of 1 plus 2x squared dx, run from 1 to 2 for x. Okay. I'll try to show you how to set up the integral, okay, and calculate the integral. I'll leave that part for some problems easy to integrate. Some other problem may be harder, and we have to do approximation. The main point for this example is to show you how to set up the integral. So you have two things in here. This is the radius r, and this is ds right here. Okay, 2 pi is a constant r times ds. All right, this one you're gonna do distribution. You got x on this, and then square root. You have two separate integrals, and have to use trig subs in here, I think. Okay, let's try another one. Say I have the same curve, 1 to 2, but this time I'm not rotating about the y-axis anymore. This time I want to rotate about the x-axis, so horizontal axis. Okay, so if I rotate that curve about the x-axis, I'm going to see something like this. Okay, and this is the area that I'm talking about. All right, hopefully that makes sense. Surface area. If you rotate a curve, same function, but this time I'm rotating about the x-axis. Okay. So we have to determine two things: the radius and ds. Okay. The radius is the distance from the curve to the axis rotation. This is our axis rotation right now, x-axis. So any point on the curve, the distance is going to be r right here. This point is x comma y. This is y. This is x. So the radius r is equal to y. All right. R is y. So you can calculate this way. Area is 2 pi integral y, because r is y. So ds, I'm going to use this formula right here. Square root of 1 plus dx over dy square times dy. So I have to calculate dx over dy in here. So we got y equal to x squared, or x equal to y to the 1/2. So dx over dy is equal to 1/2 y to the -1/2. You see, I use a power rule right here for the derivative with respect to y. Okay. It's a dy, so dy, so 1/2 outside y to negative 1/2. So we squared it up. You got 2 pi integral y square root of 1 plus 1/2 y to negative 1/2 square dy, which is 2 pi integral y square root 1 plus, this is a quarter, so 1 over 4y dy. Then you integrate that integral. Okay. Oh, and the boundary for y is not from 1 to 2 anymore. For y, it's going to be from 1 to 4. 1 to 4, 1 to 4, 1 to 4. Okay. Question. What if I don't want to do dy? I don't feel comfortable with dy. Can I convert everything to x? The answer is yes. You can do that too. Same problem right here. Okay. So if you have this dy, and you don't want to calculate everything in terms of y, you can convert things to x. What is y? Y is x squared, right? So r equal to y, which is equal to x squared, because y equal to x squared. All right. So instead of writing this way, I can write everything in terms of x. Watch me. So the area is 2 pi integral, radius is x squared, and now I use x in integral, and dx I have to use in terms of dx. I got what? Square root of 1 plus dy over dx squared. What is dy over dx? Dy over dx is 2x, yes. So 2x squared dx. And then with x, run from 1 to 2. And you should be able to calculate it. Okay? So the main idea is right here. Keep the formula. And then depends on the axis of rotation and depends on the nature of the function. You can choose either using x as a variable or y as a variable to calculate. And I think either way we're going to get to the answer. It's one way may be easier. It means that take you less time, less calculation to get to the answer. But either way is correct. Okay, and this is the end of 8.2. Let me move on to 8.3, then I'll show you more applications. What is the topic of 8.3? Application to physics and engineering. Oh, okay, so let's see. Let's show you two applications in here. 8.3, we'll be talking about two things. The centroid and the hydrostatic force. So let me talk about centroid. In here we talk about centroid about 2D object, okay? Two-dimensional objects. Say you have start with something easy. A square plate. The centroid or center of mass is the point where you can put it on tip of your finger and keep balanced. In this case, obviously, this is the center. Okay? Or you may have something a little bit complicated. Say you have a triangle. You know what? The centroid or center of mass, assuming this is the density is a constant, okay? All the material is going to be equally distributed. Center right here is got a median. You connect the two median, you're going to have the center of mass or the centroid right there. So in calculus, what you're going to see is this. You are looking for center of mass of random objects. You have a function f of x right here. Y equal to f of x. And then you bound it from a to b, x equal to a all the way to x equal to b. And you have this piece of material right here. Question is, what is the center of mass of that thing? Okay? So let me just throw into you the formula so we don't have to guess. Okay? And you guys can read the book for how to derive the formulas. It's not too hard. Okay, so how do you find the center of mass? Center of mass is going to be somewhere right here, denoted by, this is x bar, this is y bar. Okay? And we're going to show you the formula to calculate x bar and y bar. You got x bar is calculated this way. It's integral of f of x. The book used a, so it's okay. F of x dx over a, but let me write this way, integral of f of x dx, okay? And in our book, they know a equal to integral of f of x dx, so they write it as integral of x, f of x dx over a. Okay. But I'm going to write this way, it's the same. And y bar is calculated this way, 1/2 of integral f of x squared dx over integral of f of x dx. I see it. It's in the book. Our textbook is not want to write the integral twice, so it's denoted by a, so they write this way, 1/2 integral f of x squared dx over a. Again, a is the integral of f of x dx. It's the area of that thing. It's supposed to be the mass, so multiply by the density rho. But we have the rho on top, the bottom, so they cancel out. That's what it is. Okay, so this is a formula to find the center of mass. Okay, and so whenever you have a curve and then bounded by two vertical lines x equal to a, x equal to b, and you have a region, you want to find the centroid or center of mass, the same thing. You're going to apply the formula for me. You do basically 3 integrals from a to b. I forgot. A to b, a to b, a to b, a to b, a to b. Okay, you integrate f of x dx from a to b, and then what? Integrate what? Integral f of x dx from a to b without x, okay? And then 1/2 of f of x squared, so you square up the function a to b. You got 3 integrals, and you construct the fractions. You have x bar and y bar. And by the way, this stuff right here is denoted by, let's see, my. It's momentum about the y-axis. And the quantity right here, the integral right here, is denoted by mx, momentum about the x-axis. Okay, more general case. Say, instead of having one function, what if you have 2 functions? This is your function f of x, and this is your function g of x. And x runs from a to b. And this is the region that you want to find the centroid, or center of mass. Well, formula is pretty similar. X bar is calculated as integral from a to b. You can make a guess. X, right? F of x minus g of x. The top one subtract the bottom one. And then dx. Of course, the bottom integral from a to b. F of x minus g of x dx. Okay. And then y bar is calculated by a fraction. Integral from a to b. 1/2 outside already, so this is f of x squared minus g of x squared dx. Of course, have the same denominator. Integral from a to b. F of x minus g of x dx. Then you should be able to find the center of mass. And in Calc 2 right here, we make one assumption. The assumption is the density rho of the plate, the material, is going to be constant. It's going to be the same everywhere. So it's not like that region of the plate going to be heavier than the other region of the plate. No, it's not going to happen that way. It's going to be equally distributed. Okay? And then you can apply the formula. And then later on, when you guys move on to Calc 3, we face a problem that's more practical. It's what? The densities are not the same, so some part is going to be heavier than the other part. It turns out that what? Rho, the density is going to be a part of the function. We have to put rho inside the function, which is another part of the function. They come back in there. All right, so let me get an example, and I will show you how to calculate. Let me choose an easy example. So I have two curves, y equal to x and y equal to x squared. And let me show you the graph of this. This is y equal to x squared. Parabola. This is y equal to x. Okay? And I want to calculate the centroid of this region right here. Okay? So I guess it's somewhere right there. Okay?